the refinable macros and terminal boundaries in UPF 4.0, empowering soft IPs of the future. Synopsys, Cadence, Texas Instrument. Abstract System on Chip SoCs increasingly integrate numerous software intellectual properties SIPs, each with its own power management architecture. Traditional methods often fail to comprehensively capture the power intent of these SIPs, leading to challenges during the innovation and risking verification integrity. This paper introduces refinable macros and the upcoming UPF 4.0 standard, providing enhanced capability for non-intuitive refinement of SIPs power intent without the altering original designs. Refinable macros allow the IP integrators to add implementation specific details while preserving the extensive validation performed at earlier stages. And additionally, the importance of the marking SIPs are terminal boundaries is highlighted to ensure the consistent interpretations across design tools and facilitate efficiency verification and implementation. This paper discusses these new features, implementing UPF commands and best practice, ensuring case advanced data expedite development and improved efficiency in low-power SoC design. Introduction. The rapid advancement of the semiconductor technology has led to increasingly complex SoCs that integrated numerous software intellectual properties SIPs as standalone blocks, each often containing its own power management architecture, is managing the overall power intent of such SoCs presenting significant challenges. The SIPs are typically provided with their own UPF or Unified Power Format files, encapsulating power intent in a technology independent manner, enhancing the flexibility and reusability across the different technology nodes design environment. However, integrating these SIPs into larger designs often requires adding implementation-specific details during stages like synthesis and placement routing, PNR, which can risk verification integrity if not handled carefully. The existing UPF 3.1 standard, which defines a successive refinement methodology for bottom-up, the implementation flows, like defined a semantics for bottom-up verification flows involving SIPs. Additionally, the software macros defined in UPF 3.1 are intended for bottom-up implementation flows, but have restrictions that hinder necessary refinement from the SoC level, compromising optimization and flexibility. As a result, designers are often compelled to adopt intrusive method to alter the original power intent to proceed with the implementation, undermining the verification performed at the IP level. This situation forces either revalidation of the IPs, which is time-consuming and counteracts the goal of achieving faster turnaround times, or accepting the risk of introducing silicon bugs into the final product, compromising the reliability and functionality of the SoC. To address these challenges, UPF 4.0 introduces refinable macros, providing enhanced capability for non-intrusive refinement of SIP's power intent without altering the original designs. So the refinable macros enable the SIPs to maintain their validation integrity while allowing the IP integrators to efficiently refine the power intent with their implementation-specific details. By supplying UPF successive refinement methodology, integrators can seamlessly enhance the IP power intent without intrusive modifications. This work builds upon the ideas presented in our earlier paper, where we introduced the concept of the verification macros and their role in maintaining the integrity of the verifiable IP UPF through interaction. While the earlier work focused on addressing the challenges within the constraint of the UPF 3.1, this paper highlighted how the UPF 4.0 standard has evolved to systematically address these limitations, introducing the concepts like refinable macros and enhanced terminal boundaries to better support SIP integration and verification. So this paper provides an in-depth analysis of limitations on UPF 3.1 for SIP integration and introduces the key advancement in UPF 4.0. Section 2 identified the challenges with the SIP integration using UPF 3.1. Section 3 elaborated the refinable macros and their significance in preserving the verification integrity. So the section 4 discussing the implementation UPF command with best practice. And section 5 highlights the role of the terminal boundaries in ensuring tool consistency. And section 6 provides case studies illustrating these concepts in practical scenarios. This paper concludes with the benefit of the UPF 4.0 adoption for efficient and reliable SoC design. Chapter 2 is the limitations of UPF 3.1 in soft IP integration. The designing complex SoC, system-on-chip SoCs, managing power intent efficiently is crucial to do the integration of the numerous software intellectual properties SIPs, each with its own power implementation requirement. The unified UPF, the Unified Power Format 3.1 provided a successive refinement methodology to handle power intent specifications hierarchically and incrementally. So, a successive refinement methodology in UPF 3.1. This successive refinement methodology allows designers to develop power intent progressively at the design involved from the individual IP blocks to the complete SoC. This approach facilitates the collaboration between the IP providers and SoC integrators by enabling the reuse of power intent specifications across different design stages and the abstraction levels. In this methodology, constraint UPF, IP providers define a constraint UPF that outline the fundamental power architecture of the IP block, including definition of the power domains and limitation requirement, isolation, clamping requirement, and legal power state, or specified in a technology-independent manner. Configuration UPF. As the design progresses, configure UPF incorporates additional details adapting the power intent to the specific context of the SoC, such as adjusting power management strategy to align with the system-level requirements. Implementation UPF. Finally, the implementation UPF adds technology-specific information required for physical implementation, such as power switches, supply nets, and control logic for power management cells. So, Figure 1 illustrates a successive refinement methodology as defined in UPF. Figure 1 UPF successive refinement methodology. So, while this methodology promotes modularity and reuse, it primarily supports bottom-up implementation flows and lacks support for bottom-up verification flows involving SIPs. And B, bottom-up implementation flows and software macros. So in a bottom-up implementation flow, individual IP blocks are designed and implemented separately before being assembled into a larger subsystem or SoC. This approach allows IP blocks to be developed and optimized independently and leveraging their standalone power intended specifications. To support the flow, UPF 3.1 introduced software macros. A software macros represent an IP block along with its successive to be UPF, intended to be implementation and independently from the rest of the design hierarchy. Software macros encapsulate the power intent of the IP block, forming a terminology boundary and isolate the internal power intent from external modification. So the features of the soft macros: self-contained power intent. The UPF 4.0 software macros fully specify the power intent within the IP block without relying on the power intent definitions from parent or ancestor scopes. The terminal boundaries behavior. The ports of a soft macro are treated as drivers and receivers, and the power intent outside the macros does not affect the internal power architecture. Consistency interpretation. Verification tools interpreted the UPF of the soft macros in the same way as in the IP was implemented separately, ensuring consistent behavior across the different designing contexts. The advantages of using software macros. Independent implementation allow IP to be implemented independently, facilitating the modular design and enabling IP vendors to optimize their blocks without dependencies on the SoC environment. Protection of the IP integrity. Ensure that IP internal power management strategies are not altered unintentionally during integration. Consistent verification access tools reduce the risk of the discrepancy between the verification and implementation by enforcing the consistent semantic across different design tools. The example scenarios, Figure 2, demonstrate the semantic of the software macros in bottom-up implementation flow. Figure 2 is a soft macro in bottom-up implementation flow. In the figure, the software macro IP has two supply pins or its interface. The UPF is written to insert isolation cells within the IP from the source powered by the one supply to a sink powered by another supply. Since the IP is implemented separately, the isolation cells are present in the list. So when the IP is integrated into a larger block, there may be multiple instances of the IP. So in one instance, the two suppliers at the interface are connected, making the isolation cells redundant. By marking the IPs as soft macros, the verification tools can identify the IP boundaries and treat them as terminal boundaries, preserving the redundancy isolation cells even if the suppliers are connected. Note, the example of the redundant isolation cells is just the scenario, is just one scenario, and many UPF semantics can be affected by the environment, so it's important to mark these blocks as soft macros to maintain the consistent behavior across different design contexts. C. Limitations in bottom-up verification flows. In a bottom-up verification flows, SIPs are verified independently but implemented within the larger system context. So the entire SoC, including SIPs, did undergo the implementation and verification as a whole. The aligned for optimization across the design hierarchies leading to a better overall performance, power efficiency, and area utilization. However, applying the software macros to SIPs bottom-up verification flows presented significant limitations. Inability to refine a power intent, software macros prevent modification to the IP power intended from the parent scope and inhibiting necessary implementation specific refinement. Constraint on optimization. They require a standalone implementation, restricting the system level optimization and potentially limiting the performance area efficiency. Conflict with the system level requirement, the rigid isolation may not align with the system level power management strategy, so leading to the suboptimal integration. The listed verification integrity. Without a non-intrusive refinement capability, designers may resort to modifying the original UPF, compromising the IP's verified power intent. Thus, software macros are unsuitable for a bottom-up verification flows where flexibility in refining power intent during the duration is essential. The challenges in capturing power intent of the SIPs. So the UPF 3.1 lacks a suitable construct for capturing the power intent of the SIPs in bottom-up verification flows, leaving the designers with inadequate options. No marking for SIPs. Approach. Treating the SIP's UPF like any other block without a special protection. Consequences. Less mechanisms to ensure the IP's power intent integrity. requiring integrators to modify the UPF and potentially necessitating the revalidations. 2. Using soft macros for SIPs. Approach the marking SIPs as software macros imposes strict restriction. The challenges prevent the necessary refinement and optimize at the SOS level due to the inability to modify the IP's power intent. Neither approach adequately balances maintaining the verification integrity into the complex flexibility needed for the system level optimization. Need for enhanced methodologies. These challenges highlight the need for methodologies that allow non-intrusive refinement, enable integrator to add implementation-specific details without altering the original IPS UPF, preserve verification integrity, ensure refinement do not compromise the IP standalone verification, facilitate system-level optimization, align the IP power intent with the system-level strategies. Support the bottom-up verification flows, provide tool support and define its semantic for effective handling. UPF 4.0 addresses these needs by introducing refinable macros, which will be discussed in the next section. Number 3 is refinable macros in UPF 4.0. To address the limitation of the software macros in the sub-bottom verification flows, UPF 4.0 introduced refinable macros, providing the necessary flexibility of the integrating SIPs into larger systems while preserving their original power intent and verification integrity. The function and the purpose of refinable macros. Refinable macros are the new construct in UPF 4.0 that form refinable terminology boundaries. This boundary allows the SOS integrator to add implementation-specific refinement to the IP power intent during integration without altering the original UPF or provided by the IP vendors. Key attributed refinable macros. Non-intrusive refinement. Implementation details can be added without modifying the original power intent defined in the IP's UPF, avoiding the need for re-verification of the IP. Preservation of the verification integrity, the IP standalone verification remained valid, reducing the risk of the functional discrepancies. Flexibility of the system-level optimization enables alignment of the IP power intent with the system-level power management strategies, allowing the optimization such as removing the redundant logic when it's safe to do so, improving performance and area utilization. Marking IPs as refinable macros. IPs can be marked as refinable macros using set design attribute command. This command marks the IP referred to as a SIP or the current scope dot as a refinable macro by setting the UPF is refinable macro attributed to true. Practical application. Figure 3 illustrates the use of the refinable macros in the bottom verification flow. The refinable macros in the bottom-up verification flow. Figure 3. The IP is marked as a refinable macro, enabling the implementation tool to make necessary refinement during integration. For instance, after two supplies of the IPs are connected in the larger system, redundant isolation set can safely remove the optimization area without violating the IP's original power intent. The original power intent remains intact, ensuring that the IP standalone verification is still valid. Advantages over soft macros. Refinable macros overcome the limitation of the soft macros by allowing implementation-specific refinement integrators can add the details like power switches, supply nets, and control the logic necessary for the feature implementation without altering the original power intent. Optimizations side system integration enables system-level optimizations and refinements and improving the performance and area utilization. Preservations of the verification integrity ensure that IP verified power intent remains unchanged, maintaining confidence in the IP's correctness. Using the implementation UPF for refinement. Refinement for the IP's refinement to the IP power intent are specified in an implementation UPF This UPF contains only allows command the added implementation details without altering the fundamental power architecture. The details are present in section 4. Ensuring compliance and verification integrity. By combining refinable macros with the controlled use of the implementation UPF degenerates archive. Control refinement only safe and permissible changes are made to the IP's power intent, so the verification integrity preservation, the IP's original power intent, and a standalone verification remain unaffected. To assist the compliance, tools enforce constraint ensuring the refinement adhere to UPF 4.0 standard. 4. Implementation of UPF and loaded UPF implementation command. In UPF 4.0, implementation UPF allows designers to add the implementation specific details to the power intent of the SIPs without altering the original power intent defined by the IP provider. This enables safe refinement during the integration, maintaining the verification integrity while accommodating the necessary implementation adjustments. A. Allow the commands in implementation UPF so that to ensure the refinement do not violate the fundamental power architecture, the implementation UPF is restricted to specific commands and options. Table 1 lists the UPF commands and options permitted within the implementation UPF. Table 1. UPF commands and options that can be used in an implementation UPF. These commands focus on adding implementation details, creating a connect port and a net command like create a logic port and create a supply net and connect supply net and add necessary logic and a supply connection for implementation. Defining power switches using create power switches to specify the power switches needed for power gating strategies. Mapping construct the physical cell. Commands such as map power switches and map retention cell assist the logic power intent implementation with the physical library cells. Update existing power intent object. Defining power domain. With the creation power domain update, designers can update power domains with the implementation specific details like available supplies and supplies and elements. For example, adding design for test DFT logic. Adjusting power state and supplies using add power state and update and create power supply net set update to modify the power state and supply functions without altering the power the core power intent. Specifying cell insertion strategies. Isolation strategies set isolation and set isolation update enable the definition or refinement of the isolation strategy for signals crossing a power domain boundaries. Level shifting and retention. Define a level shifting required using the set level shifter and update retention strategy with set retention update. So control and configuration. Setting attribute. Set design attribute to set port attribute specified attributes affecting the implementation without changing the original power intent. Managing scope and loading. A command like set scope and load UPF assisted in the managing context and loading additional UPF files as needed. C. Using the load UPF implementation command. To supply the implementation UPF and the load UPF command with the implementation option is used. So this command loads the implementation UPF for a specified IP instance and forcing that only permissible refinements are applied. So by restricting the implementation UPF to these commands and options, UPF 4.0 ensures that the refinements are made in a controlled and non-intrusive manner. This approach allows the integrator to enhance the power intent for implementation, add a necessary detail for physical realization without altering the fundamental power architecture provided by the IP provider. So maintain the verification integrity. Ensure that the original power intent remains intact, preserving the validity of the IP standard verification. So the leverage tools support. So they enable tools to enforce the constraint and contain, check the compliance and reducing the risk of the errors during the integration. So 5. Importance of the marking IPs as terminal boundaries. In complex SoC chip design, accurately managing power intent requires not only specifying power domains and strategies but also ensuring the design tools interpret this specification consistently across the different stages of the design flow. The article aspect of achieving this consistency is marking intellectual property IP blocks as terminal boundaries. A. Isolation strategy in UPF. UPF provides two primary methods of defining isolation strategies between power domains. Port-based strategies. Isolation is explicitly defined on a specific port or signal. Designers manually specified ports requiring isolation, resulting in consistent implementation across the tools. This method has been available since UPF 1.0. Path-based strategy. Isolation is automatically inserted when a certain source and sink requirements are met based on the analysis of the cross-domain paths. This method scales better with the design changes and has been available since the UPF 2.0. However, it requires visibility of the global design and appropriate macro marking to function correctly. B. Challenges with path-based strategies. While path-based strategies simply UPF specifications and adapt well to design changes, they introduce challenges. The global design visibility. Tools must analyze the entire design to identify the cross-domain paths, which can be computationally intensive in large designs, and the consistency between the simulation and synthesis. Without the proper boundaries, different tools may interpret the isolation requirement differently, leading to the inconsistencies. And functional correctness. Inaccurate path analysis can result in missing or incorrectly inserted isolation cells and potentially causing the functional errors. These challenges necessitate a mechanism to control the scope of the path-based analysis. C. Terminal boundary semantics. UPF addresses the challenges by defining terminal boundary semantics, which stop cross-domain tracing and specified boundaries and rely on a boundary constraint. So the driver and receiver applies no boundary port. Tool consider the supply conditioned at the port of the boundary without analyzing the internal details of the IP. Macro marking by marking IP blocks as a macro designer inform tools where tools apply the terminal boundary semantics. D. Types of macros. UPF defined three kinds of macros that form the terminal boundaries. So the soft macros, UPF 3.1, representing IP intended for a separate implementation, then encapsulating their power intent. Hard macros, UPF 3.1, pre-implemented IPs with fixed functionality and power intent. Refinable Macro, UPF 4.0, introduced two for SIPs, allowing the non-intrusive refinement while preserving the original power intent. All three macro types require tracing to stop at their boundaries, relying on a boundary constraint to ensure the correct power management. E. Benefit of the marking IPs as terminal boundaries. Marking IPs as terminal boundaries provides several advantages. The control path analysis. Tools limit cross-domain path analysis to within the terminal boundaries and reducing the computational complex and improving the scalability. Consistent tool behavior, ensuring the verification and synthesis tools integrated power intent consistent, reducing the risk of the discrepancies. Parallel processing enables tools to partition the design and macro boundaries and facilitating the parallel and processing and faster analysis. The functional correctness. By relying on the boundary constraint, tools accurately insert necessary isolation levels using cells and maintaining the functional integrity. F. Practical implications. In design employing path-based strategies not marking IPs as terminal boundaries can lead to inconsistent isolation cell insert across tools and stages. Simulation and synthesis. Without terminal boundaries, simulation tools might insert isolation cells differently from the synthesis tools and causing mismatches. Complex design. Large designs with numerous power domains and IP blocks exacerbate these issues, making the terminal boundaries essential for manageability. Okay, figure 4 is simulation and synthesis methods without terminal boundaries. So figure 4, the illustrated is common inconsistency between the simulation and synthesis when the terminal boundaries are properly defined. An IP block implemented as a standalone macro has two input supplies powering its internals. When instantiated multiple times in SoC, there are scenarios where these supplies may shorted by connecting them to the same supply. In the SoC, within the IP, crossing between logic powered by the supplies are handled by isolation strategies that insert the isolation cell. If the source and a sink supplies differ. During standalone synthesis, the isolation cells are inferred at these crossing based on solely in internal conditions. So the isolation cell are they included in the analysis for instances of the IP in the SoC as it uses the macro analyst and cells. So this discrepancy between simulation and synthesis can lead to the Swiss issues, such as incorrect clamping of the isolation cells during normal operation in instances where supplies are shorted. Marking the IP as a soft macro emphasizes terminal boundary semantic, ensuring the simulation respects the presence of the isolation cells and demonstrate how simulation tools account for macro behaviors. This consistency catches potential issues during the RTL simulation, ensuring reliable verification of the final hardware. This highlights that macro markings are crucial for functional correctness and tool consistency in a UPF-based design. Table 2 summarizes the key features of UPF 4.0 discussed in this paper and their benefits. Table 2 and Chapter 6 is a practical applications and case studies. To illustrate the practical benefit of the refinable macros and terminal boundary marking, we present an example demonstrating their applications. Example: integrating a predefined IP with refinable macros. A predefined IP has gated always on a domain. The gated domain is switched through a SoC implemented power switching. The implement isolation between the AON and gated domains and validate each power intent. The SoC integrators needs flexibility in choosing the isolation location based on placement and routing PNR requirement without altering the IP's original power intent. IP's UPF. IP UPF and the IP, the AON and PGD power domains and specified isolation strategy without location option, allowing the SoC integrators to define the isolation location based on implementation needs. So the SoC implementation UPF. So the SoC integrator defined the IP's isolation strategy by specifying the location option. You need to refine our macro semantic. And the integrator can make this refinement without altering the IP's original UPF. Set SoC level UPF parallel IP1 UPF. By using the load UPF command with the implementation option, the SoC integrator ensures that all refinements comply with the UPF 4.0 standards and that the IP original power intent remains intact. Benefits demonstrated. Flexibility in implementation. The SoC integrator can specify implementation details like isolation, location without modifying the IP's original UPF. Preservation of the verification integrity. The IP standalone verification remained valid, avoiding the need for revalidation. Tool assist compliance. Tool enforced constraint, ensuring the refinement adhere to UPF 4.0 standard. Chapter 7. Conclusion. The introduction of the refinable macros and enhanced terminal boundary definitions in UPF 4.0 represent a significant advancement in a low-power design for complex SoCs by addressing the limitation of UPF 3.1. These new features enable designers to integrate pre-qualified SIPs more efficiently and safely, without compromising the verification integrity. Key contributions of the UPF 4.0 include non-intrusive refinement capability, allowing the implementation-specific details to be added to SIP's power intent without altering the original definitions, preserving the extensive verification performed by IP provider. The flexible terminal boundary definition, providing mechanism to mark IPs as refinable terminal boundaries, facilitating the efficient partitioning of the design and enabling tools to manage complexity effectively. Enhanced tool support, empowering the design tools and enforced constraint to vary compliance and assist in implementing the power management strategy and reducing the likelihood of errors. By adopting these methodologies, designers can achieve improved design quality, enhance optimization opportunity to lead to the better performance, low power consumption, and efficient use silicon area, reducing the development time, streamline the integration of the verification processes, accelerate development cycling, helping companies meet aggressive time-to-market goals. Risk mitigations. Preservation of verification integrity minimize the risk of the functional errors and contributing to more reliable and robust products. The evaluation of the UPF standard reflects the industry responses to growing the complexity of the SoC design and a need for efficiency, scalable methodologies. So Refinable Macros in UPF 4.0 offer a balanced approach, providing the necessary flexibility of the implementation refinement while safeguarding the original power intent and verification effort. Okay, today I read this DVCON2025 paper, the Refinable Macros in Terminal Boundaries in UPF 4.0, empowering of the IPs of the future. Thank you for your time. See you next time.